Okay. Let us start with another sum. In the last class, I could not finish it because of the lack of time. This is the problem. Let us do it here now. First, the problem is, what is the temperature limits of an ammonia refrigerating system? Here, in this problem, we are using a ammonia refrigerating system itself. It is ranging from T2, that is T2, the higher temperature, and T1, that is lower temperature itself. It is arranged between this temperature 25 degrees centigrade and minus 10 degrees centigrade. And another condition is given, the gas is dry at the end of compression. Now we have to calculate the COP and the cycle, assuming there is no undercooling, in the liquid system. Use the following session, following in the following table for the properties of the ammonia itself. Now, here, this is the typical problem, although simple, but here we have to find how we can do this type of problem itself. Here, what is given is T1. Actually, we have to draw now here I am supposed to first draw this TS diagram as well as pH diagram. That is a TS diagram itself, entropy and temperature T. The formation is generally like this, and this is like this. Cycle is more or less like this here. Now, share screen. Share more. Now, that is the diagram, and we have to make the pH diagram. That is pressure P, it is H or enthalpy. Here, the curves are like this, and this is the condition of our cycle itself. That is 2, 1, 3, 4. Now, you see, in order to calculate COP, we have to know H1, H2, H3, and H4. Means enthalpy at the point 1, at the point 2, 3, and 4, we are supposed to know to make COP, because COP stands for output by input, Here output is the refrigerating effect, which is ranging from 4 to 1, that is H1 minus H4, and input is the work done by the compressor itself, which is ranging from 2 to 1 itself. So that is here you have to do H1 minus H1. So you have to calculate all these 3 4 as per your available data within data given to your problem. Now, what is given in the problem is we know the temperature T1, that is the lower temperature T1, lower temperature that is given here. This is T1, and this is given here, that is equal to T2, or T1 is equal to T4, that is equal to T4 is given here as minus 10 degrees centigrade, minus 10 degrees C, which is equal to minus 10 plus 273 equal to 263 degree K. And temperature T2, the higher temperature of the cycle, T2, higher temperature, is equal to, that is also equal to T3, is given as 25 degrees centigrade. So 25 plus 273, which is equal as 298. So both the temperatures are known to us. Now we have to find out how we can calculate this H1, or whether it is stable or not in your given problem itself. Now, what is given in the problem is the liquid heat at T1 and T2. What is given? Liquid heat given, liquid heat at T1, which is given as T1, that is lower temperature, that is at 263 degrees centigrade. What is the T1 is equal to 135 degree 0.3737 kilojoule kg plus kg. And what is this? This is the liquid heat at T1, and whether what is this? Is it H1? H1 is what is the liquid heat? Means the heat. If the point is on this liquid line, this is the liquid heat itself. But this point is not on the liquid line. Board is at the wet region. So H1. So this is not H4 itself. So this is not H4. Now, what will be the H1? And H1 is the enthalpy at the point 1 itself. And what is given here is another important thing, the HF3, which is HF3. HF3 is the enthalpy at the point 3 here, which is on the wet vapor line curve. It is on wet vapor line. It is on only vapor line. So just 1 second. So HF3 will be the enthalpy at temperature T2, higher temperature T2 on which is equal to HF3. F for fluid, 3 is the point 3 here. So this is the point 3, which is here the liquid heat at the point 3. That is 298.9 degrees centigrade, 298.9 degree Kelvin to kilojoule per kg. Next, HFG2. Next comes HFG2. When there is F and G, means it is the latent heat. Every this term, abbreviation yes here is stand for latent heat, and 2 means the point 2 itself. So this is the point 2. So latent heat will be given by from the distance between from here to here. The latent heat, which is disturbed, which is taken out of the outside atmosphere when the condenser refrigerant condense from vapor to liquid in the condenser reservoir. So this HF3 is given, HF3 is equal to H4 HFG2, which is given as the latent heat at the point 25, which is given as 1166.94 at per kg, and HF3 H3 is equal to HF3 because at the point 3 it is over on the liquid line. So the enthalpy at the point 3 is equal to the enthalpy at the enthalpy given on this vapor line at temperature T2 is the enthalpy at the point 2 itself, which is given as 298.2 kg, 9 kilojoule per kg. Next comes what we are going to do with the entropy itself. What is given? Entropy at the point 2. SF2 is given. SF2 is the, from the entropy chart, it is the point 2, which is the fluid point. It is not on the vapor itself. So SF2 is given as the liquid entropy, and it is the entropy at the point 3 itself. So which is given as 1.1242. That's also kilojoule per kg degree Kelvin. And HF1. And what is HF1? And SF1 will be the entropy at that fluid line, which is at the point 1, and it will be more or less somewhere here, It is the temperature entropy is given here, which is given as HF1 is a 0.55543 kilojoule per kg degree Kelvin. And another thing is given HF1, which is the fluid. What is HF1 is also given. HF1 135. There is a liquid heat at 0.4, which is given as 135.57. But this is not equal to H1. H1 is here. H1 means fluid line is on the fluid line, means somewhere here. But it is not required for at this moment because we need H1 to know our factor of safety. And HFG1 is given as 1297.68 kilojoule per kg. So, but this HFG1, as it is given as F and G, it is the latent heat, which is given as 1269 at the temperature T1 itself. So, it is latent heat of combustion from H2 to H1, but it is not neither H1 nor H4 itself. So far we have got only one point, that is H4, which is HF3 H4 is here, more or less. H4 is here, which is equal to H3, which is equal to HF3, 298.9 degree Kelvin kg per kg. Only this is given in the problem. Other three, H1, H2, we have to calculate itself. So this is the point, enthalpy here, and at the point here, entropy we are supposed to do. Now, let us, in order to know to do this problem, you see, at the point 4, at the point 1, both are in the wet region. So both HF4 and HF1 is the mixture of wet vapor and liquid vapor itself. And so it has some certain fraction of it is in vapor form and certain fraction of it is in liquid form itself. So at point 1 and 4, refrigerant is in liquid and vapor form itself, which means it is neither standing on the liquid line, not coming on the vapor line, but it's coming in between them. So part of them is in liquid state and part of it in the vapor state. So we have to know the fraction. No, we have to know the fraction of vapor. That is, say, x1. Now, how will you do? And from the temperature entropy diagram, you see S1 is equal to S2 itself. S1 is equal to entropy at the point 1 is equal to entropy at the point 2. So we don't know initially, because at the point 1 entropy is not on the vapor line, but at the point 2 entropy is on the vapor line itself. So it is also given here as SF2 means 1.12, 1.142 kg for itself. So what is entropy at the point 1? Is given as S1, say S1 is equal to entropy at the fluid point SF1 means some entropy somewhere here. If there is a fluid point somewhere here in the fluid itself, and SF1 plus X1 fraction of the liquid vapor here multiplied by HFG HFG1, the latent heat of vaporization, divided by the temperature itself, that is T1 itself. So here SF1 is given as this is 0.45, the entropy at the point 1 itself. So 0.5443 plus X1 is unknown to us, and HFG1 is given here 1297 divided by the temperature T1, which we have calculated here as 263 degrees centigrade. 63 degree. Now, which will be reduced to 0.5443 plus 4.934 x1. Similarly, entropy at the point 2. So this is equal to the entropy at the point 2 itself. Entropy at the point 2 S2, but it is not given to us. We have given liquid entropy, which is entropy at the point 2 itself, but here is HF3. entropy at the point. This is the point here where we know the entropy, but because entropy at liquid refrigerator is given at high temperature, which is given as 1.122 itself. So you have to do it again here. So S2 will be SF2 entropy SF2 entropy at the point 2 plus temperature rising enthalpy SFG2 HFG2 means the latent heat divided by the temperature T2 itself. This is the latent heat from 3 to 2 HFG2 at the point to reach from 3 to 2, and the temperature is there at equal to T2, the high temperature itself. So as SF2 is given 1.1242 plus HFG is given as HFG2 is given as 1166.9 1166.94 divided by temperature T2, which is given calculated here as 298. So this is equal to 5.04. Okay. Now here we see S1 is equal to S2, as at the point 1 is equal to S2. It is totally vertical line. So for entropy at the point 1 and 2 is equal. So this is equal to 5.04 is equal to 0.5443 plus 4.934. 4.934 x1. From here, x1 we are calculating the x1 itself is equal to 0.91. Thus, we can now calculate the entropy at H1. The enthalpy at H1 which is the enthalpy here at this point, because we know now fraction we know HF1 enthalpy at the point 1 in liquid state. So here at we know the liquid state enthalpy, which is given here 1.36 enthalpy plus x1 multiplied by HFG, the latent heat at the point 1 itself. So HF1 is here 135.57 plus 0.91 into HFG1 1297.68, which is given as equal to 13316.26 kilojoule per kg. And H2 is in the same way enthalpy at H2, which is the enthalpy here. This is the point where which is given is HF2 is given HF2 enthalpy at the fluid at point 2. So somewhere here, this is the HF2 itself plus here the latent heat of evaporation at this stage T2 is given as 14 LHFG2. Latent heat is here 116.94 HFG2. So that is equal to HFG1 is 1298.9. HF2 is equal to HF2. 298 plus HFG2, which is also given as 1166.94, which is equal to 1465.484. kilojoule per kg. Thus, the coefficient of performance COP is given as H2, H1 minus HF3 or H4 divided by H2 minus H1, where we have got, we have calculated H1, we have calculated H2, we know H3, we have known H3 and we know H1 itself. So if we put all them, that will be equal to 1316.26 298 298.9 divided by 1465.84 minus 1316.26, which is equal to 6.8. That is the answer of this question. Let us go to the next problem itself. I put that, let me without sharing. Let us go to the next problem. Here, a vapor compression refrigeration system is works within the pressure limits of 60 bar, that is P1, P2, that is P2, and 25 bar, that is P1 itself. The working fluid is the first just dry at the end of compression, and there is no undercooling of the liquid before the expansion valve itself. So what condition is given? It is just dry at the end of compression, means it will stand on. This is the end of compression at the point 2. It is just on the vapor light here and here. So here already it is given now, and it is not, there is no undercooling of the liquid before the expansion valve. So expansion is going on here at the point 3. Expansion is started, and it is started on the liquid itself. It is not cooled somewhere and started from anywhere from here. And we have to do the COP. We have to calculate the capacity of the refrigerator, and if the fluid rate is at the rate of 5 kg per minute itself. Now, here, of course, like our previous problem, we have to calculate, we have to find out what is the H1 and H2, H3, H4. Here also, of course, we have to find H1, H2, H3, H4. So if you know, you can know, then you can calculate. COP as which is given as H1 minus H2 as well as H1 minus H3 itself, H2 minus H1. Now, what we have to, how we can do, what is given here, we have to examine one by one. P2 and P3 is given. What is P2? P2 is there. It's the pressure enthalpy diagram. This is P2. Here it is P2, and this is P3, and this is P2. Both are on the same horizontal line, so this is same. or P or P2 is equal to P3 itself. And so that is given at 60 bar, and P1 and P4, that is on this, we have it, pressure is P1, it says that pressure is same as equal to P4, so P1 is equal to P4, and both are given. And temperature from the chart is given in Kelvin calculator. So higher temperature T2 is given here as 295 degree K, and lower temperature is given as 261 degree K itself. And there are other things are given: enthalpy at the enthalpy liquid and vapor, entropy at liquid and vapor at two different temperatures. Here, temperature at the higher temperature is when it is liquid form, and when this vapor part is in vapor form. So what is telling us in the chart is that HF3, which is the point here, this is equal to HF3, is that more or less is equal to H4. Then it is on the same vertical line. This is equal to H4. Is equal to H4, and this is given as the enthalpy on the liquid line at the liquid stage at higher temperature, which is given as 156.96. So it is put it like this: HF1, the enthalpy of the fluid at the point 1. So it is supposed to be somewhere here, but not, this is not H1 itself. HF3 is not equal to H1, but H1 is also given. And Hg2 is equal to H2. HF of the gas is Hg2, and we say that as per this working process is just dry at the end of compression. So we can say HFG2, Hg2, enthalpy at the gas at the point 2 means enthalpy of the vapor here, which is equal to H2 itself. So this is also given, and Hg1 at the point enthalpy at the gas is equal to 333.8. This the enthalpy of the gas is somewhere here, point should be somewhere here, but this is not equal to H1 itself. So we have to calculate H1. And entropy at the point 2, SF2, is the entropy here is given, that is entropy at the vapor state 1. Entropy at the point 2, and it is vapor state at 60 degrees Kelvin. So this is given as this 1 point. This is this is F2 here. This is given here as in liquid form. No, this is given F2. F means in liquid form in entropy, which is given 0.554. HSF1 is given as 2.226. This is the entropy somewhere here. And SG2, entropy at S2, this is the entropy here at S2 is given as 1.003, entropy at the gaseous state. And SG1 is the entropy at the gaseous state at the point 1. But it is not on this line, but it is somewhere here. So with these inputs, what we will do, now we know entropy at the point 1. That is given as S1. S1 is supposed to be the entropy of the fluid state at 1 plus the fraction of the vapor multiplied, fraction of the vapor present in the mixture multiplied by the entropy at latent heat of entropy at the point 1 itself. The latent heat given here. This is the difference between SF1 plus X1. This is the difference between the entropy at the point 1 in gaseous state minus entropy at the point F1 at the fluid state itself. That's SG1 is this one, F1 plus SGFK. All this value except X1 is given. So we have got equation at the file where this are 1.02 X1. That is equal to S1. And we know S2 is given as SG2, entropy at gaseous state at the point 2 is here, which is given as 1.03352. So this is put it here. So if we use these two equations, then it will get the value of X1 itself. Now, the enthalpy at the point, what is the enthalpy? We know the enthalpy at the point 1. We have to know that. So H1, enthalpy of the fluid at the point 1 is given to us, plus we have calculated the fraction of the vapor in the in the refrigerant liquid vapor refrigerant mixture multiplied by the latent heat of vaporization of the mixture itself at temperature T1. So you put all this value because H1 is given minus HF1 is given. So difference is equal to the latent heat of vaporization. So we put the value of here, and all these things to get the value of H1 itself. So we got H1, we have got H2 and HF3 itself. So if you put all of them one by one in the refrigerant test, we get the entropy equal to 4.36 into HCOP is equal to 4.306 itself. Now you have to find out the capacity of the refrigerator itself. The heat extracted or refrigerating effect produced per kg of refrigerant. What is the heat extracted or refrigerating effect produced per kg of refrigerant? This will be H1 here minus H3 or H1 minus H2. It is H1 is the enthalpy at the end of evaporation, and HF3, which is equal to H2 enthalpy at the beginning of evaporation itself. We both have calculated both of them, so we put them 2.96, and this is given as H2 as H1 and 266, which is given is 266. This is calculated, so here we put it here minus 151 HFP at the point 3 in the liquid stage, which is equal to 1.596, which is given here. So 1.4.96 itself. Now, since the fluid flow is at the rate of 5 kg, so the total heat being extracted is the fluid flow by 5 kg per minute multiplied by the fluid extracted per kilojoule per kg. So that will be equal to 5.7485 kilojoule per minute itself. Thus, the capacity of the refrigerator, which is given as the energy required to transform divided by 210, the enthalpy required to convert 1 kg of ice into water itself. So capacity is given by this is the maximum heat it can extract per minute, and this is the heat required to extract per minute. So this divided by this is equal to 2.74 ton. This is the capacity of the per minute, and 1 ton, 210 kilojoule per minute, which is given as per the value of the definition of 1 ton. We don't have much time left for here. Let us stop share itself. Okay, I'm finishing the class by today.